colour is crazy. For example, at the end of this talk, I'm going to convince every person in this room that these three colours up here are identical. I work down the road at the National Physical Laboratory. It's a big measurement institute. And what do you do when you've got A-levels in art and physics? You go and measure colour. That's what I did. And this was one of the first things that I was asked to measure. This is NPL black. It's a piece of nickel phosphide etched with a really powerful acid, eating away, drilling holes deep into the substrate. It looks like the Grand Canyon, doesn't it? Light goes in, gets trapped, and cannot come out. This is black. It's the blackest black you'll ever see. In fact, you can't see it. It's that black. And it was so black, we couldn't measure it. We just said, it's blacker than we can measure. It was a disaster. The most incredible thing is that it was invented by Dr. Brown. Some of the colleagues at NPL, the National Physical Laboratory, said it's a rubbish black because they weren't interested in what it looked like to us, but what it looked like in the infrared region of the spectrum. And we can't see every type of radiation that we call light. This is the spectrum that we can see. We have a peak of sensitivity in the green, but it dies off beyond violet. Ultraviolet radiation would damage our eyes. It would literally etch away, destroying the subtle biology of its power. And at the higher end of the spectrum, infrared, there's just not enough welly in the light to excite our eyes. So we have this range of response to light. And light is a human perception. Colour is a human perception as we see it. So I'm going to just show you a little odd trick now. Here's an elephant, or a picture of an elephant. Please stare at the square in the centre of the elephant. In fact, concentrate not just at the square, but at one tiny one corner of it, okay? Stare, stare, stare. Now, you're probably told off generally for staring at things. Women, television. But these things generally move. It's quite unusual for you to stare at something as static as this. So an odd case is happening, and something odd will happen as a result. Is it still there? Now, I can't take a photograph of that with my colour measuring apparatus. That's an image I've etched into the retina in your eye. Your eye has got bored of seeing a pink elephant, and parts of your retina have switched off. That switching off carries on even when you're not looking at anything, and so you see an after image. You see an opponent colour, as it's known in the trade, or a complementary colour. Designers use these. Let's have fun looking at another one. You recognise the shape. You know what's going to happen. I've learnt the complementary colours of this well-known flag, and by staring at one part of this thing, I'd suggest the tip of the elephant's trunk. Stare, 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 don't look left, right, up, down, don't wiggle yourself, don't. Just stare, concentrate. And the image starts to go glassy, doesn't it? And in time, you will become blind to that image. You really will. Your eye will just switch off. The negative version on your retina or in your brain of that image will overwrite everything and you'll see nothing. It'll be sensory deprivation. I shall put you out of your misery. Blink. Look around the room. If it's still with you in 2 days' time, it's nothing to do with me. Colour is extremely persuasive. And when it comes to measuring it, which is what I was given to do as a job, it's impossible. Because it's part of a human experience. And we use this all the time. Here are some glasses of liquid, and I'd love to do this in the flesh, but I'm just going to have to pretend. This is a thought experiment. Think that you have these glasses of liquid with sugar in them, perhaps put a bit of fizz in there too. Let's colour them. Oh, PowerPoint is wonderful. Stare at those individually and you can almost taste the difference. Is that weird? And believe me, if you did physically taste those, even though they were physically exactly the same, apart from the colour, you would taste them differently. There is this cross-sense thing going on. Because colour is built into your experiences, you associate it with things that you've experienced in the past. And it's really difficult to try and program computers and robots that see things and are required to tell you what the colour of something is to include this in that experience report. Here are two images of faces. A man and a woman. No, they're not. They're the same picture. They're the same slightly androgynous image, but I've changed the contrast on it. And so one of them looks distinctly female, one of them looks distinctly male. And this is just tinkering with the contrast on them. Imagine what you could do with colour. There's the paper reference. What is colour? Well, colour is something that modulates the spectrum. It reflects or emits or transmits some wavelengths of colour that we can see, more or less than other wavelengths. It tinkers with the spectrum. And there are many, many different ways of doing that. They're all reported in this beautiful book here. And I've just drawn a couple of images there to show you the sorts of colours that result from all these odd chemical and physical things going on. There are some more. There are 15. And just incredible. We live in a colourful world. And yet there's enormous confusion about it. And it starts when we're at primary school and we're required to teach or be taught what the primary colours are. What are they? Oh, already I hear 4 numbers being... It's a trick question, of course. Well, let's start off with the question, what is a primary colour? A primary colour is... they're sets of elemental colours which you can build to make all of the colours that exist. Fantastic. And that themselves can't be mixed to make each other. Okay? And there's a conventional wisdom that tells us there should be 3 primary colours. 3, because we have 3 types of sensor in the eye that resolve colour for us. So I can create a colour solid like this that contains all of the colours that exist. They're all in there, in theory. But there is a theory. There is a theory that there are primary colours, and it kind of lets us down a bit. Let's think about projection systems, televisions. They have dots of red, green, and blue light. They are the additive primaries. And by switching on and off these lights, we can create any colour we like. So were we to switch off the blue lights there, as viewed from a distance, I think 3 times the distance of this lecture theatre, you'd see that not as dots of red and green, but you'd see that as a uniform area of yellow. So those are the primary colours when you're adding light, the additive primaries. And here we go. We can mix together red and green, and somewhere in the middle we'll get yellow. And we can make this go further and further, and we can create all of the colours that exist. Oh, no, we can't. There are some colours missing. Those deeper violet blues. We can't reproduce them faithfully on a television screen. And I have to tell you, this is fudged. What you're seeing up there, I'm not projecting the real colours in the right place. It's just a sort of an attempt to render the colours that we can see. There is no system that can reproduce all of the colours brilliantly. It's just an artist's impression in a way. So this is a colour gamut, if you like, of colours on an additive system like a television set. And you can only really create those colours inside there. The psychedelic ham you're looking at, by the way, is based on the average perception of 17 human observers who were experimented on voluntarily in the 1920s. 7 of them down the road in Teddington at NPL, and 10 of them, 10 more because they're cheaper, they were students at Imperial College London. And out of them they got this colour model. And this very colour model is in more or less every computer that we have today, checking colour and making sure that what you scan in, what you photograph in, what you display on the screen and what you print out, there's a continuity of colour there. And it's a tricky thing because some of these things are using additive systems to present the colours on the screens, and then some are, I think, using this subtractive system that I'm about to explain to you. And so there's the gamut of colours that you can achieve with additive system. And let's try, this is a typical inkjet output. That's really rather naff, isn't it? That's not a great range of colours. If you tweak the system, if you have a really nice paper, good reflectance, you have some really good inks, You can push the boundaries out there a little bit. But what you can create is not a great collection of all the colours that exist. So the first thing, what are the primary colours? Well, there are no magic 3 sets of colours that will create all the colours that are possible. It's impossible. But we are told that the additive primaries are red, green, and blue, and you mix all these together. Mix all together, you'll get white. And the subtractive primaries are these ones, cyan, magenta, and yellow, as used by print makers and artists. They subtract light rather than add light. And how does that work? Well, here's a piece of magenta on ink on some paper. We'll shine some light onto it and we'll see what happens. In fact, what I'm going to do first is take the paper away. You have to bear in mind that the ink is actually slightly translucent. The ink, the light comes on, penetrates the paper, the ink, and is absorbed. Some of it is absorbed. Remember, I said colourful things are things that tamper with the spectrum. So this particular stuff has absorbed the green. It's minus green. Magenta is minus green. Can you see where this is going? Cyan is minus red. Yellow is minus blue. So we are taking away red, green, and blue light. So if we take away red, green, and blue, we take away everything, what are we left with? Black, yes. Possibly not the blackest black that ever there was, but a bloody expensive one. Do you know how much inkjet printers cost? Inkjet ink is phenomenally expensive. It's more expensive per milliliter than the most expensive champagne you could ever expect to buy. So the cheap option is to then use this 4th ink, black, which is actually dirt cheap. It's just carbon, really. So that's why there are 4 inks used in the printing system to take away light, to take away red, green, and blue. I know what you're thinking. Well, I don't, but I thought I'd put this slide up anyway. How do I know what you call orange isn't what I call blue? Does everybody see colour the same way? Well, the answer is sort of tied in with this graph here. This does look rather as though someone's thrown a psychedelic bedsheet over some old furniture. And in fact, it is a combination of these graphs here. These are the 3 responses of 3 different types of sensor in your eye to different types of light. One gets excited more by the blue end of the spectrum, and the other 2 one more by the reddish and one more by the greenish part of the spectrum. But it's quite subtle, isn't it? That's what's going on inside the retina in the back of your eye, and the different responses from these 3 species of cone sensor in your eye, that's what gives you the resolution of colour in your lives. Now, to measure how people see colour, we have to build rigs like this. This is my boss, Julie. In 1989, we built this phenomenal colour mixing system. We were mixing light, and we were trying to work out how people saw light. So there you go. And essentially, you might think, OK, we'll work out how people see light, and then we'll build a sensor that is responsive to the red part of the spectrum, the green part of the spectrum, the blue part of the spectrum. That'll tell us what the colour of things is. Great! Except not everybody sees colour the same way, do they? So there's a sort of unhappy average thing coming in. And that's where colour starts to become crazy. Colour is also affected by many things. My first job was actually as a botanist. And I was required to match the colours, or describe the colours, of plants, chrysanthemums specifically. And we shipped these chrysanthemums in, and we looked at them at Royal Horticultural Society colour charts, like we've got here. And it was really, really important. It was written into the measurement protocol that A, I wasn't allowed to be colourblind, and B, we had to look at them inside these colour matching cabinets, which controlled the quality, the type of light that was being used for the experiment. Now, if I'd have done the experiment, the colour matching experiment, looking at these colour matching charts, comparing those against the colour of the chrysanthemums, if I'd done that in daylight, I'd have got a different result to if I'd done it in tungsten light, to if I'd have done it here, or under LED lighting or compact fluorescent. The lighting is just as important. Colour is a product of the light source, something that changes the colour of the light source, and our eyes. All of those change all of the time. So here's a bloke looking at a blue object, and let's illuminate it with some blue light, and hey, it appears blue. So let's change the colour of the object to red. What colour is a red object going to look like under blue light?
Black.
Black. Fantastic. You've passed GCSE physics question. This is actually put in as a standard question. And then they'll ask, what does that look like? Yeah, again, black. Because there's no blue light being reflected by green things and red things. Is there? Sometimes there is. This is what I call the Trevor dressed in black demo. I used to be in a rock band. I was actually the road manager. And Trevor would go on stage dressed in a menacing black outfit, illuminated by blue parkans, thundering blue light onto him. And what colour did he look? Red. What? The point was that the lights that they were using, not only were they letting blue light out through the filters, but they were letting a little bit of red light through. Otherwise, the filters would have just burnt out. Blue lights are the ones that always burn out in blue filters on theatrical lights are the first ones to burn out because of the heat coming through and melting them. So they let through all of the infrared, or as much as they possibly can, and a little bit of the red too. And Trevor's clothes, I don't know why, he didn't look at them under red light, reflected, they were supposed to be black, but they had a little bit of reflectance, and so they ended up looking red. Now, if I answered that in GCSE physics, I'd fail. Also, things fluoresce. You know about fluorescence? Things come on at one colour and come off at another. That's bizarre. This is the house I was born in. My parents are in the audience. Thank you. You were there. And this is my grandmother's house, actually. It was a two-generation thing. And the one thing I really remember from my grandparents' house was Lego. Used to build things in Lego, and in the kitchen, the blues just looked different to if you took the Lego into another room. The blues looked vibrant and just a completely different colour. So I'd carry the Lego from one room to the other and just think, this is incredible. What's happening to the blue? I tried to reproduce this experiment at MPL and completely failed because I couldn't find the particular type of fluorescent tube that my grandmother used to use. They're illegal now. But for fun, I switched on the UV light in my colour matching cabinet, and I got this. Look at the yellow. Just incredible. But the blue is quite vibrant there, isn't it? You can really see something happening in the blue. The blue seems to fluoresce, or at least reflect in an odd sort of way, particularly under that type of fluorescent tube. I also noticed something else. Look at the reds. Under all but the bottom left, the bottom right, the reds look fairly samey. But what's going on there? That's fluorescence. That's definitely fluorescence. Some Lego bricks fluoresce more than others. It's the same with teeth. When they try and match the colour of your teeth, it's important that they match, for false teeth, important that they match the degree of fluorescence that your teeth have too. Otherwise, down the disco, piano keys. So colour changes. It changes with the type of lighting that you have, but also personally, the way we experience colour varies too. Here are the brackets of generations. My father and my daughter going for a lovely walk in a bluebell wood, deep in thought. And I know that they're seeing completely differently. Because my dear daughter, how old was she then? 2, yes, 2 years old. I won't humiliate my father by asking him how old he was then. But this was earlier in the year. My daughter still receives a little bit of violet-y, ultraviolet light radiation into the back of her eye. It's nearly all gone now. My father, those days have long gone. In fact, the amount of blue light going into his eyes, sorry Dad, not much these days. The eye yellows in time. It just yellows up. Just gets yellower and yellower and yellower, which doesn't really matter to us. It's as though we've got yellow spectacles on. We just get used to it. It's like changing the white point. But it means that blues become less vibrant to us in older age until we have the cataract operation. Then it's, whoa! Colour changes the lighting level. Again, back in that bluebell wood, this is what the bluebells look like during the day. But at night, when we start to lose the ability to use our colour sensors, another system comes into play. We're equipped with night vision. Did you know that? We have night vision. We have rods that are more excited by lower levels of light and can give us sort of an appreciation of what's going on. We can't see colour, but we can see contrast. We can see objects just about as we stumble around in starlight or moonlight. Do that next time. Very low lighting levels. Look how not colourful things are. So at dawn and dusk, a bluebell wood, the blue and the violety blue of the bluebells just becomes violently light, incredibly light. So colour changes according to illumination level. Also to do with how much area you've got. I don't know if you've ever done decorating, but you get these tiny little swatches and you think, yeah, that will look good. And then you completely paint the whole of your room and it looks completely different. Literally, the way we see colour varies according to how big an area we're seeing of it. And those original experiments done in the 1920s at NPL were a 2-degree field of view. That's a thumb at arm's length. Some more experiments done in the 1950s looked at a 10-degree field of view. That's a hand at arm's length. And they found completely different perception of colour over that larger area. So next time you're looking at colours for your room, go like that. There's a thing called chromatic adaptation, and it's the reason why we can adapt to different types of light source, whether we're in a cave lit by a flame, or whether we're outside lit by the sky. And we had fun in the old days at NPL where we had this big metal vessel that every now and again we'd walk into and just change the internal colour of the lighting. You'd go in there, it would be bright green when you walked in. Then your eyes would just get bored with it in the same way that your eyes got bored with that elephant image. And you just think, oh, it's white. And then you come out and the entire world had gone pink. Here's a cool one, simultaneous contrast. Again, I defy an instrument manufacturer or someone trying to measure colour with robots to get this to work. It gets quite complicated. Can you see? This is a reproduction of something I made. And please go home and make this yourself. In latter years, I've done it in Excel, just by colouring different cells. But there's only one pink thread there. But can you see it looks different according to what it's next to? Colours are affected by what are around them. And artists know this to great effect. So if you want to make yellow stars look yellower and blue skies look bluer, put them next to each other. If you want to make greens look greener and reds look redder, then paint those red flowers on that green grass. And one of my favourite artworks is this, well, it's like a bouncy castle, but you walk around inside it. It's called Colorscape by Peter Jones. And you just wallow in the colour. It's just incredibly vibrant colour as you go in there. And you see incredible things happening as you move from one zone to the next. A lot of simultaneous contrast stuff going on in there. This is almost my last slide. I saw this artwork 2 days ago for the first time. And again, it's one of these odd, tricky things where there are actually only 3 colours there. But they look like they're more because of this adjacency thing. So I did promise you that I would show you 3 colours that looked identical, but they're not. So let's start with this. It kind of depends where you are. But if you're really, really close up to this and you look closely, you can see a continuity of colour going between the green and those inner rings. Okay, so the inner rings up the top are green, and that square is green. So let's move the square down, and that continuity is still there. That's still the same green going across there. That top green is the same as that bottom green. Do they look it? Do they look it? A few. Okay. Let's have this picture here. The eye here and this square here, do they look as though they're kind of the same colour? There's a continuity of colour rattling across there. And in a funny sort of way, that colour there this colour here is kind of the same as that colour there-ish, okay? All I'm going to do is move that square in the middle to the right. I'm not going to change its colour in any way. I promise you, if we measured that colour, it would remain the same all the time. But you watch it. As it moves, something odd will happen to it. it appears to change colour. That's nothing to do with the display system up there, I really promise you. So there are those three colours. They are exactly the same. I'm going to stop. Thank you. It's crazy!